student, very good morning. Today we will discuss the concept on continuous periodic function. It is basically one important topic in real analysis, and also you will see the questions which is exactly given in CSIR net from real analysis section. So when we are talking about continuous periodic function, so we need to think about the two terminology. One is continuous and other is the periodic function. So that means the function is continuous as well as periodic function. Periodic. So the basic example is sin x. If we take the function sin x, x belongs to R. So this function is basically continuous periodic function with period 2 pi. And that is another example if we take say fx equals to cos x, x belongs to R. This is also continuous and periodic function. So now if we think about the continuity, so now first recall is definition of continuity. So when our function is basically called continuous, a function if R to R is called continuous, R to R is called continuous on R if and only if for all open set U in R, F inverse U, that means the pre-image of U, F inverse U is also open set in R, where F inverse U, this is basically all those x belongs to R such that fx belongs to U. So this is basically the concept of F inverse U, that means the pre-image of U. Or we can say the function f R to R is called continuous if for all closed set K in R, F inverse K, this is closed in R. So we can say the first one or the second one, and we can define the continuity in the topological point of view like this. Now if we think about the periodic function, so when a function f R to R is called periodic, this is recall 1, recall 2, a function if R to R is said to be periodic on R, if there exists a number p greater than 0 belongs to R such that f of x plus p, this is equals to fx for all x belongs to R. And here this p is called, a period of f. If there exists a least positive constant t, such that or among all the periods like P, 2P, 3P, then it is called fundamental period. Fundamental, or you can use the terminology primitive or basic period. So as for example, for sin x, so fx equals to sin x belongs to R. This is basically a periodic function with fundamental period 2 pi, because 2 pi is the least positive constant among all the periods, so that sine of 2 pi plus x equals to sin x. So now one important result on the, if the function satisfies continuous as well as it is periodic, then it is called the continuous periodic function. So next recall 3. If a function f r to r is continuous and periodic, then it is called continuous periodic function. So there is one important recall. This is also, you can say, the theorem. The theorem is a continuous periodic function, is bounded and uniformly continuous. Furthermore, we can say that it attains its bound. So that means it attains supremum and infimum both. So if we think about the proof of this theorem, so just you notice that f is continuous and periodic. Suppose p greater than 0 is fundamental period of f, because it is a periodic function. So p greater than 0, it is a fundamental period of f. So from this we can write f is continuous on the closed interval 0p, because it is continuous on R. And if we think about the fundamental period is p, so it must be, p is obviously greater than 0, so it must be continuous. Again, we know the recall, every continuous function, the recall is every continuous function on a closed and bounded interval, that means on a compact set AB, is uniformly continuous. So from that we can write f is uniformly continuous on the closed interval 0p. And also every continuous function, that is another recall, every continuous function on a closed and bounded interval closed and bounded interval is bounded. So here it is continuous on the 0p uniform continuous, and we also say that the f is bounded. So that means there exists a positive real number m greater than 0 such that mod of fx less than equals to m for all x belongs to 0p. But what we have to show? We have to show that our claim is, we need to show the f is bounded on R. So this is our claim. So now we just take mod of fx. We can write mod of fx as mod of x minus np. Why? Because it is a continuous, it is a periodic function, continuous periodic function. So for all x belongs to R, there exists n belongs to natural number such that x minus np that belongs to closed interval 0 to p. So we can replace x by x minus np as it is a periodic function. And f is periodic with period p greater than 0. So that means here x minus np belongs to 0p. So we can write this is less than equals to m by the above condition. So that means what we get? We get exactly mod of x fx, this is less than equals to m for all x belongs to R. And that implies f is bounded on R. Now we have to prove f is uniformly continuous. So this is claim 1. Now we have to prove, this is claim 2, f is uniformly continuous on closed R. How we have to prove f is uniformly continuous? So also for all epsilon greater than 0, there exists delta 1 greater than 0 such that if xy belongs to closed interval 0p with mod of x minus y less than delta 1, then mod of fx minus fy, this is less than epsilon by 2. Why? Because f is uniformly continuous on the closed interval 0p. So this is basically a definition of uniform continuity. So now we just consider let delta equals to minimum of del 1p, and if mod of x minus y less than delta, without loss of generality, we assume x less than equals to y. So then there are two cases. There are two cases. First, case 1. Case 1 is basically x comma y belongs to np plus p for some n. For some n, this is our case 1. And hence, then fx minus fy, that modulus, we can write f of x minus np minus f of y minus np, and that value, because xy belongs to np plus p, that value obviously less than epsilon by 2. Now we'll move to the case 2. X belongs to np minus p, comma np, and y belongs to np plus p for some n. Then we can prove that then mod of fx minus fy, that modulus equals to less than equals to mod of x minus np minus f0 plus y minus np minus f of 0. So this will be epsilon by 2 plus epsilon by 2 equals to epsilon. That means in either case or in any case, we have fx minus fy, that value less than epsilon. And consequently, we can write f is uniformly continuous on R. So this is very, very important question. If a function is uniformly continuous periodic, then we can prove that f is bounded and uniformly continuous and it attains its bound. So this result is very, very important. Based on this result, one question is given on Csir mathematical net examination, June 16. The question is like that: let f R2R be a continuous function and fx plus 1 equals to fx for all x belongs to R, then which of the following is true? Option A, f is bounded above but not bounded below. Option B, f is bounded above and below and f attains its bound. Option C, f is bounded above and below but may not attain its bound. And option D, f is uniformly continuous. Just you recall the previous result. The continuous periodic function must be bounded and uniformly continuous and it attains its bound. Here just you see the question paper, f is continuous, this is given. Now we need to think about the periodic function or not. So it is given fx plus 1 equals to fx for all x belongs to R. So that means f is a periodic function with of period 1 and 1 is greater than 0. So that means f is a periodic function and it is given continuous. So continuous and periodic, and we know continuous periodic function means it is bounded. That means f is bounded above or below and f attains its bound. So option B is correct. Option A, f is bounded above and not bounded below, that means f is not bounded, but continuous periodic function always bounded. So option A is false. Option C, here it is given may not attain this bound. We know if f attains its bound always. So option C is false. And option D, f is uniformly continuous. This is right. So thank you so much.